A lot has happened since we were last on YouTube. We've got a whole workstation with our familiar Haas HL1 lathe, a new workbench, new cabinets. Oh, of course, this giant mezzanine above my head. And most excitingly, this behemoth, a Haas VF2 SS. With a 4th axis, this is still a fairly recent acquisition for me. Everything is still in wrapping, and we need to get it unpacked and powered. After getting the machine in place, we went ahead and ran conduit to it, as well as the Haas lathe. We've got a 3-phase panel in place and already pulled our wires to both machines. But there's an issue. Our incoming power supply is single phase. 200 amps of it, but with 1 phase missing. What if we make our own phase? Can we do that? Now, in the past, I've gotten around this issue by using a variable frequency drive, which acts as our phase converter, giving us a digital 3rd phase where there is none. Unfortunately, they don't make phase converters for machines of this size. This Haas has a 15 horsepower spindle, and this mill has a 20 horsepower spindle. Thankfully, there is another way to generate 3-phase power, a very old way. And what you do is you use a 3-phase motor and power it by single-phase power, find a way to start spinning the shaft, and once the motor starts, it will generate your 3rd phase. Now, as much as I would love for this to be just a giant motor that I have for demonstration purposes, it is not. In fact, it's the size motor that we need to generate enough of a 3rd phase to power the both of our CNC machines. How many horsepowers, you might be wondering? Well, the nameplate says 40 of them at 96 amps. And that leaves us with a little bit of an issue. You see, although you can run a 3-phase motor on 2 phases, trying to start a 3-phase motor on 2 phases is quite a bit more challenging. The most common approach is to use what's known as a capacitor start system. By taking 2 of your leads of single-phase power and applying it to your 3rd lead across a capacitor, you're able to, let's say, jump start the motor. A pretty good way to do things on a small motor, something say 56C size or in this realm. But for a large motor like this, the current drawn startup would not only probably blow my local transformer, but my neighbors would know about it. And that's something I don't want them to know about. Now, other than the capacitor start method, well, I guess I could just spin this up by hand every single time, though I suppose that would probably get tiring. Then it hit me. Like most garage enthusiasts, I've got a whole bunch of old motors sitting around. This one happens to be single phase, which means I can start it using the power I have coming out of my wall. And why not use this motor to maybe somehow spin this motor, and then once it's spinning, I can connect my 3-phase, and voila! I have 3-phase power, and lots of it. In addition to the single-phase motor, I was able to scrounge up this awesome little motor tensioner, which makes my life a whole lot easier because I don't have to make any slots. Connecting the 2 motors was a little bit challenging. This has a really small 5/8 diameter shaft, and this guy, as you can tell, is a very large 2 1/8 of an inch diameter shaft. Trying to find pulleys that are compatible between the 2 is a challenge, to say the least. A lot of smaller motors use an L-belt style pulley, which is deep and wide, and large motors tend to use these smaller belts, but more of them, narrower. I think it's H-type or F-type. Somebody will have to correct me on that. Thankfully, SK sleeve pulleys are available in a 5/8 of an inch shaft all the way up to 2 1/8. I think this is actually the largest you can fit on here. And through the power of the internet, I was able to find 2 6-inch pulleys. There's a slight mismatch in size between them, and considering these are both 1800 RPM synchronous motors, they really should be identical, but this is what was available. It's cheap and it'll work well enough. Now, like most of my stuff, this motor came to me at the wonderful price of take it out of my yard, please. So before we put all of our eggs into this basket case of a motor, we should probably take some time and evaluate its condition. Now, mechanically speaking, when I spin it by hand, it spins smoothly. There's a little bit of bearing noise, but it looks like we can grease this, and I bet you it hasn't been greased in a long, long time. Electrically speaking, I have no idea if it runs. I was told it does, but who knows? Now, seeing as how we're trying to make this motor run, I can't just plug it in, but we can use some electronic wizardry and take a good guess at the actual condition of things. Now, clearly these wires are frayed, and that's going to be problematic. We'll have to replace this lead. Now, we'll first check the resistance between ground, which is the green wire, and one of our phases. And it looks like we're not reading anything on the meter. Just to check, you can see if I connect my 2 probes, we have continuity, a beep, and an ohm reading of 0.1. Our first phase shows nothing, which is good. Our second phase also shows nothing. And finally, our third phase also looks good. The next thing we can check is the resistance between the phases. Now, we expect some resistance here. We're seeing 0.2 between the first 2 phases, 0.3 between the second 2, 0.2 between the last 2 phases, which should be a good sign. Let's see if we can't help these bearings out a little. Hopefully some of that got in the bearing. Oh wow, that already sounds better. I imagine those were pretty dry. Why don't we get the shaft cleaned up? Seems as if somebody had painted over this at some point. Spritz of liquid love. Now, these quick disconnect pulleys are pretty sweet. When you insert the pulley, there's a taper on it, and it clamps up on the shaft for a very, very nice, tight, secure, concentric fit. Now, since I'm just doing a temporary fit up, not going to insert any bolts. Just want to get a sense of motor and pulley placement. Now, what I'm thinking is that I'll be able to fashion a plate to take this small single phase motor and mount it coming off of this shelf right here. I'll have to pop this box open, see what connections we need to miss with our drill. We can probably fashion ourselves a nice bracket that comes off, mounts our motor, as well as our tensioner. Get our pulley mounted on our smaller motor, and go from there. Much better. And just like that, we've got our new pulley mounted. Now, in order to have these pulleys line up, this motor has to be offset quite a bit. Our tensioner bracket will have to sit somewhere approximately here. Look at that. It's completely potted. This cover weighs just about as much as the pony motor we're going to use to start it. Unbelievable. Now the good news is that there's nothing up in this corner that we're planning on tapping. We'll confirm our wiring is for 240 volts. So low voltage, you can see here 2, 8, and 4 should be together, 3, 5, and 9, and 1, 7, and 6. Looks like 5 and 8 are together, T7 and T4, 6 and 9. So it looks like it's currently wired for high voltage. We'll have to fix that. Now, as far as the mounting plate goes, let's take a look at our scrap pile and see what we can't scrounge up. Got this old shelf which could be used as a frame, maybe the side section. Now this plate was a cover for concrete smoothing, polishing, leveling machine, and the people who did my concrete left it here and didn't want it back. This will be perfect to be cut up and used for this phase converter after we clean it up. I've got this mount positioned roughly how it's going to go. You can see one of the mounting bolts will miss the bottom plate, but that's okay. I can just put in another hole over here. Let's notch this corner out, round off some of these edges. Now I'd prefer to do this on the Bridgeport, but it's not really in the right position at the moment. So we're going to do it on the good old trusty Rockwell Delta drill press, since we just got to pop a few holes in anyway. Start with the spotting drill. You know, this drill press is actually the first machine tool I used on my own. I must have been, I don't know, 7 or 8 with my grandfather's. My dad was pretty liberal with my shop access. Start with the 3/8 drill bit. It's a bit fast. It's actually a woodworking model, so it does spin a bit fast for metalworking. 300 RPM is the lowest it'll go. I forgot to hit record on the first rivet nut, but I'll demonstrate the second one here. Pretty simply, you thread your rivet nut onto your installation tool, insert it through your bore, squeeze extremely tightly with it something this big, about right there. Release, unthread it, just like that. Got it nice, threaded insert. Super easy. Now that should all line up nice. I've marked our hole positions from the mounting plate. I'll center punch them, pilot drill them, and then drill to final diameter before tapping with the 3/8/16 tap. They're all pretty loose fits, so I've got some room to play with. This appears to be cast iron or cast steel, so it's nice and easy to drill. No lubricant required. Next, we'll drill it 5/16 of an inch. This is the pilot size for a 3/8/16 tap. Definitely cast iron. Now we can run a tap through those. Got a handy tap socket. Would have some limited clearance here, so. And the thing about using these is you have to be careful not to side load them. Give ourselves some time. I've never tried power tapping with this, but only one way to find out if it works, I guess. Famous last words. That does work. And let's just put a quick chamfer on those while we're at it. Now, I did make a small error. Accidentally mounted these riv nuts upside down. It actually worked out because I needed to space this out from the panel anyway. So we can take our fasteners, bolt this guy down. Screws are a bit long, but it's functional. And since we're so cantilevered, it has some wobble. I think what we'll do is we'll put a bracket off of here to one of these mounting bolts, or come straight down to whatever mounting we have down there. And we should be able to offset that pulley enough to line it up with this guy, no problem. You can see we're definitely too bouncy, so I'll have to support this bracket. Off camera, I've removed the single phase motor and reinstalled the cover just to get a sense of where I can mount a bracket to better support this. Angle iron for my scrap pile. See, I bolted up the bracket lightly. Yeah, I think that'll work. Got that tacked in place. Already that's significantly stronger, but what we'll do is we'll get it up and burn it all in. That actually turned out fairly well. It's significantly stiffer than I was expecting it to be, which is never a bad thing. Nice. Now we can get back to wiring up our connections, running some fresh wire, and getting a frame built underneath this. We've gone ahead and got all of our pieces cut to size, and this is approximately the layout that we're going to have for the frame for the rotary phase converter. We'll bolt the motor directly to these C channels on top. The bottom square tube is here to just give us a little bit extra height, and so that we can fit our pallet jack underneath this frame if need be. I will be putting leveling feet underneath these as well. I haven't decided if I want to use rivet nuts here. I do have 1/2-inch rivet nuts, but they might be a little hard to press in. We'll just have to see. Let me go ahead and get this welded in place and be with you all shortly. let's go ahead and get this frame painted. I've been accumulating parts for this project for quite some time. Many of them I found used in excellent condition on eBay. Oftentimes companies will have a lot of overstock of otherwise good components that they just need to get rid of, and some fantastic deals can be had. This magnetic contactor, for example, is rated for a 50 horsepower motor. If I were to have bought this new, it would have probably cost me a couple $1,000s. I only paid a couple hundred, I think 200 or so, so you really can't beat it. It also happens to have an auxiliary contact on it, and I could add a second if I needed as well. Now, this isn't everything that I need for this phase converter, but it's the grand majority of it. We've got a start and stop switch, power distribution, a contactor for the main idle motor, a smaller contactor for our pony motor, some time delay relays, some panel meters to see what's going on as far as our voltage and amperage are concerned. We've got 3 of them for each phase, and a whole bank of capacitors that we'll use for phase balancing. Can't forget copper lugs, and we've got a whole bunch more of those in this cabinet if need be. And the idea is to fit it all into this sweet cabinet that I also got off of eBay for a great deal. 24 by 24 with the necessary depth we needed of about 8 or 9 inches in order to fit that massive contactor. And very nicely, it still includes a mostly untouched back panel that we can mount some DIN rails and wireway on. Now, having spent many years doing control systems, I've learned that it's easiest to simplify your problem before getting started. In this case, our pony motor started rotary phase converter is really quite simple. I've narrowed it down to approximately 5 steps, with some of those steps having maybe 1 or 2 actions taking place. First, we're going to hit the start button. When we hit that start button, we're going to want to turn on our pony motor, which will be done using this contactor. We're going to wait for our system to be up to speed, about 30 seconds or so, and because we have that delayed, we're going to need a timer relay. After that 30 seconds is up, we're going to want to do 2 things. We're going to want to engage our idler motor using our big contactor. And we're also going to want to turn off our pony motor, which means we're going to need a second timer relay in order to control this contactor. Assuming that everything went correctly, we'll end up with our pony motor stopped, our main idler motor running, and a working 3-phase system. We will of course have to do some phase balancing using our capacitor array, which we'll get to later, and we're going to monitor that using our digital meters, but really that's the entire system. The last step in the system is going to be hitting the off button and having the entire system shut down. Now normally I would start with a CAD model, but considering that I'm only planning on making one of these phase converters, it's far easier to just pull the panel out of the box that I have and start laying things on it and kind of get a sense of where everything should be placed. Starting with the main components, let's get our big contactor in place. In addition to being the contactor for the main motor, we're going to use this contactor combined with these dual ported lugs in order to take our incoming feed wire and step it down to a reasonable wire size for a control panel. Based on the layout of the box, the incoming power has to come in at the top. I could come in anywhere I want, whether it be this corner, this quarter, or right in the middle, so I have some freedom here. I think I'll start laying things out and then decide on the final placement once I get everything in place and DIN rails mounted. After getting everything laid out on this panel, I immediately have some concerns. First and foremost, my original idea of mounting all of the capacitors on DIN rails using some handy brackets I 3D printed might not work that well. You see, what I'm concerned about is that I can't really mount that many. I do have more depth in the box, so I might find a way to mount these capacitors perhaps on the bottom. So for the time being, I'm going to not worry about it, set them off to the side, and get the controls in place before I worry about all of my balance capacitors, seeing as how I don't really know how many I'll actually need. And I think I'll start by mounting these lugs to make sure that I have them in the right position, and then I'll grab some DIN rail, some wire way, and lay things out a bit more closely. I realized before I got too invested in this contactor that I should probably test it. It was sold to me as a working unit, but let's give it a try. This contactor coil is rated for 120 volts. So I'll just use a little cheater cord to provide it that. And turning on the switch. Haha! Appears to work. That's too satisfying. Some contactor hum. Usually cycling it a couple times gets rid of that. I realized that the switch actually has a quick release contactor, which is freaking awesome. Upon closer inspection, I noted that there was some corrosion on these coils. So I'm going to try rubbing that off. It's not that bad, actually. Never thought I could quick mag swap a contactor, but here we are. Let's get that wire back up and give it a try. Moment of truth. Much quieter. It's about as good as you can expect from a contactor of this size and this age. After going back and forth on this for a little while, this is ultimately the layout I came up with for the panel. I've got my main disconnect on the right side with a ground lug, which I'll attach to this panel after removing all of the paint from it. Distribution here, which I can easily connect to the incoming wires. Contactor for the smaller pony motor. 2 time delay relays, 1 timer on delay, 1 timer off delay, which will be used to start the pony motor first, followed by the big contactor for the main idler motor. Some wire trowel to get the wires where they need to go. And then 2 racks here for capacitors. And if need be, I can always put some capacitors in front of them, as I do have some depth left in this panel. I'll be using some number 10 by 1/2 inch self-drilling sheet metal screws to attach everything, aside from the ground lug, which I'll drill a 5/16 hole for and bolt up. I also decided it would be a good idea to put together a quick little diagram, just using some ladder logic to make sure I get everything where it needs to be. I labeled the ports for each relay just to make things a little easier. I did try making a schematic of this nature, but I don't really think in this way. Ladder logic works better for me. Still, I've made some handy notes like how the timer wiring is connected and a little reminder of how to make a latching relay, even though I've done it 100 times. For now, I'll have the main controls off to the side here, just laying on the bench. There will be one mounted on the face of the box, as well as one mounted on the wall somewhere in my shop, so I can start it either from inside the phase converter shed or in the shop. And I'll use this indicator light here on the 3rd generated leg, so it'll only illuminate when I know that I have the phase converter running. I'm going to go ahead and get everything fastened and then begin wiring. I usually like to begin wiring my panels by putting in my larger gauge wires. In this case, it's really just the distribution from my incoming wires to my distribution section over here. For this, I'll be using 6 gauge wire, which is the minimum that I can connect to these incoming terminals. 6 gauge will be plenty of amperage for what little controls we have here. I think this pulls a couple of amps, and the biggest load at this point is going to be the 1.5 amp solenoid for the big contactor. I'm applying some aux guard to all of the connections to make sure that they don't have any corrosion over time. This wiring went on for a couple of hours, and to be honest, it wasn't all that interesting. Let's get some work done on the enclosure instead. See if we can't find a position for these panel meters. A couple of studs I need to look out for. I'm going to go ahead and pull this panel back out for the time being. Next, I'll just add a starting hole. These are a little bit too small for the jigsaw. Nice. I won't push that all the way in yet. Might need a little more filing. Let me get the others cut to size. Got all of the holes cut for the panel meters. They might need a little bit of fiddling, but they're approximately to size. Now I'm just going to go ahead and mount the start-stop switch right here. Let's go ahead and get these panel meters wired into place. We'll start with the current transducers. I'll just be using some 18 gauge wire I have and soldering them to the existing connections. Normally I prefer to use crimp connections, but in this case soldering will be just a little bit easier. It's not really a high vibration environment, so it shouldn't be an issue. Finally, we can heat shrink these. Next, I'll route these all the way to the terminals that connect my balance capacitors. But first, I'll get the current transducer soldered in place as well. Here are some of those nice, neat solder connections for the current transducers. Get them heat shrunk on, and then tie these looms together. With all of the wires for the panel meter soldered, we can go ahead and get it in some wire sheathing. I've got all the connections made. I've separated the pairs for each transducer, but I'm actually not sure which one is which, so I'll check them with the multimeter before I connect them up. But at this point, we are ready to start balancing. We are still waiting on a 220 volt coil, so I'll still be using my little cheater for the time being, but otherwise this is more or less good to go. Now, as far as connecting this, I do have the cable that I'll be using. It's 4-0 aluminum, which is plenty good enough for 200 amps that I want the system to be rated at. This only pulls 100 amps, but regardless, that's what we're running. This stuff is quite a pain to unravel, but seeing as how the disconnect switch is in the far corner, I think I'm just going to unravel it in here, connect it to the corner, and run the phase converter sitting on the floor right here for the time being. This will be going outside in the shed behind where the toolbox is, and we have to run some 3-inch conduit to and fro, but for the time being this should work. We should probably be careful. No touch. As the old saying goes, trust, but check. As you can see, the incoming line here is very spicy. And here, not so spicy, which is good. We'll just close that while we're working on this. Now we won't be using the neutral line on the first run. I'll later be taking this cable and cutting it in half. It was simply cheaper to buy one length of quadruplex instead of getting triplex and then quadruplex. So we'll just snip it short and leave it unused. I think what I'll do is, I should be able to pull this up, get each line in carefully. This connection is now live, so we do have to be cautious. Just gonna clean up my area slightly. And we're doing this together, folks. This is my first start. Moment of truth, when I hit the start button, this motor should turn over. I won't turn on the main motor just yet. And contact. Woohoo! So there what happened is I didn't engage the main idler, so it shut off as intended. Next, I'll repeat that, but as soon as we're up to speed here, I'll engage the main motor and we'll see what happens. 3, 2, 1, contact. We have 3-phase, baby! Could you see my lights dim? Oh, that's awesome. Today is a good day. With the phase converter now functional, I hooked up the current transducers in order to monitor the amperage between each line, and I spent the next few hours adding balance capacitors in order to bring up the voltage in the generated leg. I won't show the entire process, but the general idea is to keep adding capacitance until you see the generated leg be about 8% higher than the incoming voltage. Adding capacitance is pretty simple. You take the two legs of each capacitor, which are of course rated for the run voltage, and apply the capacitance between the leg that we want to see increase in voltage. There's a general formula that's popular on practical machinists that a lot of people follow, and it did help me get close, but ultimately in the end, once I had the unit up and running and connected to my machinery, I did have to remove some capacitance from the system. Every phase converter is a little bit different, and the load that you supply with the phase converter will also affect how much capacitance you need in the system. After balancing the system for a little while, I ran out of capacitors, but I got very close with my values. I was seeing 260 volts on the two generated legs and 240 volts on the incoming leg, which should be right where I want to be. I went ahead and ordered some larger capacitors to replace the bank of capacitors I had built up. The new capacitor should be more reliable, and also I want this all to fit inside of my panel with ease. I'm going to go ahead and switch out the existing capacitors for new capacitors and continue tuning a little bit more. But once I get the final values, I'm going to button everything up and ultimately connect this phase converter to the 3-phase panel. I use my capacitance meter in order to check the value of my bank. This will give me an exact value that I can try to match more closely with my replacement capacitors. That's showing 316 microfarads. Now checking the new capacitors. That one's spot on at 75. 75 as well. I'll be surprised if these all come out exactly where you're supposed to be. Usually you'll see a bit of variance. Haha, 74. So one's, 75. It seems we're there. And we also have an additional 7.5 that we can add. So moving forward, we'll just assume that these are all the same capacitance. So what I'll do is put all of these in parallel, and then I'll also probably connect a few of the fans to get to 316 microfarads. I'll begin by connecting all my commons. And I'll connect these 75 microfarad capacitors first, which should bring us up to 300 microfarads. Grab our meter and double check. And we're right at 300. Now to get us to the 315 we were at before, we can simply add in 2 of the smaller capacitors by connecting the fan to the hermetic side. Just like so. And that should bring us right to 315. Spot on. And then we'll of course connect it back to the system. I'm waiting on a couple of more capacitors to arrive in the mail, but in the meantime we can restart the system and use the additional capacitance we have here to do our final balancing.
With the system balanced, there is only really one thing left to do. I've waited a really long time to turn on this machine. Immediately upon first power up, we were presented with a few issues. The burn in this monitor is a lot worse than I remember it being. Possibly from sitting so long unused, things just kind of degraded. I pushed the power up restart, only to be presented with the Z-axis drive fault. This was something I had feared might be an issue. Being over 30 years old and sitting unused for the past year and a half, there was always a possibility that some of the capacitors in the drives might just suddenly, let's say, blow up. Seeing as how there's nothing to it but to get to it, I started fault finding. The drive itself showed a fault, and the scorch marks weren't really all too encouraging. I removed the drive, brought it over to my bench, opened it up, and lo and behold, I found that a couple of tantalum capacitors had blown. A new board is nearly $1,000, so I'm going to have to find a way to fix this. Unfortunately, that's going to have to wait for our next video. Thanks for tuning in to Rocan Motor Company.